Problem number 6, we've got a surface S, which is part of a cone. Z is equal to 6 minus the square root x squared plus y squared. Above the plane, z is equal to 0, together with the disk in the xy plane. X squared plus y squared is at most 36. So this surface is the closed surface. So it includes both the top part of our cone and the bottom base. So we have this vector field F, and we want to find the flux. That's marker ain't so hot anymore. Let's find a new one. We want to find the flux of F over surface S here. This integral, it's over a closed surface. Let's put a little loop there. And so it's going to equal, we should know, by the divergence theorem, the triple integral over, let me use E here as a letter, the region inside of the surface. So it's the triple integral over the inside of the surface of the divergence. There we go. So what do we need to do? Step 1 is to set up, find the divergence. The divergence of F is equal to, this gives us x squared. The partial derivative of this respect to x is x squared. The partial derivative of this respect to y gives us y squared. Partial derivative of this respect to z is 0. And so this then is our integrand. But we should realize that it's probably best to translate this into cylindrical coordinates. So bounds on theta, r, and z. So it's going to be one full loop around the circle. So theta runs from 0 to 2 pi. The biggest that we can have r squared is at most 36, so r is between 0 and 6. And then z runs from 0. The xy plane will be z is equal to 0 to 6 minus the square root of r squared. That's 6 minus r. And so this integral ends up as the integral theta runs from 0 to 2 pi, r runs from 0 to 6, z runs from 0 to 6 minus r of x squared plus y squared becomes r squared. And then r, we still have that factor of r to throw in here, dz, dr, d theta. So the problem doesn't ask us to evaluate it, it just says set it up. This is our setup. Okay, so that was problem number 6. For problem number 7, so we have this vector field here. Our first task in part A is to compute the curl of this vector field. So the curl of F is equal to, let's see, I hat, j hat, k hat, partial derivative with respect to x, y, and z of yz, negative xz, and yx. And so this gives us, let's see here, partial derivative with respect to y of yx is x, minus the partial derivative with respect to z of negative xz. That will give us a plus x there. The partial derivative with respect to z of yz is y, minus the partial derivative with respect to x of yx, so y minus y there. And then the partial derivative with respect to x of negative xz will be minus z, minus the partial derivative with respect to y of yz, so that will be minus z here. So this becomes 2x, 0, and negative 2z. Okay, so here is our curl. So then in the second part, we are asked about x squared plus y squared plus z squared is equal to 13. X is at most 3. So this surface right here, let's draw this surface. So it's most of a sphere. So let me just draw a sphere here, but x is at most 3. So over here is x is equal to, not 3, square root 13. Square root 13 is a little bit bigger than 3. So the idea is that there is a circle right here that slices it in the plane x equal to 3, and we want everything behind that. Let me maybe try drawing the picture one more time. So there is some opening here, and then it's a sphere behind that. Okay, so we want to find the flux of the curl of f through S with respect to the outward pointing unit normal vector field. Okay, so the flux of the curl of f, the integral over our surface S here of the curl of f dot ds by Stokes' theorem is going to equal the integral along the boundary of S of f dot dr. So we have to parameterize the boundary here and then compute the requested line integral. So first off, which way does our boundary go here? Our boundary is going to go, we want as we traverse the boundary, to have the positively oriented side of our surface to be on our left. So it's going to be in this way. As we view it kind of head on in this direction, it'll be oriented clockwise. So let me just get rid of that pen off further away. So in the YZ plane, it looks like this right here. And this is the circle. This is the circle. X becomes 3 squared plus y squared plus z squared is equal to 13. So subtracting 9 from both sides, y squared plus z squared is equal to 4. So this is a circle of radius 2. We'll parameterize it, r of t, in the following way. So x is always 3. X is always 3 in this slice right here. And then we want 2 cosine t and 2 sine t for y and z, but because we want the clockwise orientation, not the counterclockwise, y is 2 sine t, z is 2 cosine t will be the correct orientation here. So then r prime of t will be 0, 2 cosine t, and negative 2 sine t. Okay, so at this point then, what do we have to do? We need to evaluate, we need to substitute into f, not into the curl of f, but into f. So f of r of t becomes y times z becomes 4 sine t cosine t. Negative xz becomes negative 3 times 2 cosine t, negative 6 cosine t. Y times x will be 6 sine t. And so then, excuse me, when we do a dot product of f with r prime of t, this dot this, we would get 0 minus 12 cosine squared t. And then we would end up with minus 12 sine squared t, and this just ends up as minus 12. So this integral, let me just squeeze it in right there, integral from 0 to 2 pi of negative 12 dt, of course that's negative 24 pi. Okay, so that is the final answer to part B squeezed in. For part C, let D be the portion of the sphere, x squared plus y squared plus z squared is equal to 13, where x is at least 3, this side of it. So it's the missing part of the sphere right here. Find the flux of the curl of f through D with respect to the outward pointing unit normal vector field. So we would do the same thing here. The only difference here is that because now our surface is on this side, this part right here gets oriented counterclockwise, not clockwise. And so the only thing that changes here is that this changes, and the answer to part C ends up as positive 24 pi. And so we see we end up with adding this and this together, we get 0, and that makes sense because we know that the flux of the curl of f over any closed surface, which would be if we glued together S and D here, it would be a closed surface. We have to get 0.